Okay, in this video we're going to do some odd problems for the 5-1 assignment on slope fields. And here it says determine a solution, determine whether the function is a solution to this given differential equation. Now, do you remember what this notation here is? That y, it looks like y to the fourth, but it's in parenthesis. Remember when we're doing derivative notation, you got y prime, double prime, triple prime. After that, we use a number like an exponent, but we put it in a set of parentheses. That way we know it's not an exponent, it is derivative notation. So let's see here. We'll look at both of these. Y for 13, y equals 3 cos x. We'll find if it is a solution to that, and then we'll do 15. If you don't want to watch my solution to 15, of course, you could always go to calcview.com, go to 5-1 in the calc book, and look at problem 15. Here, one of our friends from Calc Chat will also solve it for you. So let's see here. So we are going to need a fourth derivative and the original function. So let's see here, let's derive at once, y prime, derivative of 3 cos. Okay, the derivative of cos is negative sine. And we need to derive it again, y double prime. Derivative of sine is cos, so the negative 3 comes along, sine derives to cos of x. And let's derive it. Third derivative, triple prime, derivative of cosine is negative sine. So the negative will switch that back and it'll go to a 3 sine of x. And one more derivative, the fourth derivative of y, sine derives to cos. So that'll be 3 cos of x. And look, we got right back to where we started. You know, our fourth derivative is the same as the original function. Now, we don't need the derivatives in the middle here, so we can get rid of those. And let's see, the fourth derivative of y, that is our 3 cos x, minus 16 times the original y, that's 3 cos x. Does that equal 0? Well, let's see. We've got 3 of these, and then here we're going to minus 48 more of them. So that'll be 3 cos minus 48 cos. That'll be some negative 45 cos. It's not equal to 0. So that is not a solution. Here's number 15. So again, we've got the original function y. We're going to need the fourth derivative. Here we are going to need to use the chain rule each time we derive. So our first derivative, e to the negative 2x, will derive to itself. And then we'll chain rule our inner function. That'd be times a minus 2. So when we derive again, this coefficient will be hit by a minus 2, so it'll switch signs and double to a 4. The third derivative, this will multiply by a negative 2, so now it's negative 8, e to the negative 2x. And our fourth derivative, multiply this by a negative 2, so now it's to positive 16, e to the negative 2x. So let's see. Y to the 4, or the fourth derivative of y, that is 16, e to the negative 2x, minus 16y, minus 16 times y. And our original y function is e to the negative 2x. Does this equal 0? Yeah, we got 16 of these minus 16 of the same things. That will equal 0. Check. That worked. 19 and 21. Determining if it's a solution or not. We have our differential equation here. X times y prime minus 2y is equal to this. So I'm going to just stash this down here. And let's see. We've got y equals x squared. So the derivative of that y prime is going to be 2x. So let's put that in here. X times y prime. I've got x times, here's my y prime, 2x, minus 2 times y. But now y is out. We can just replace that with an x squared. Does that equal x cubed e to the x? Well, let's see here. We got a 2x squared minus a 2x squared. Does that equal x cubed e to the x? Well, there's no e to the x over here. If we subtract those, we're going to get 0. So if our original differential equation was this equal to 0, we could say yes to that. But that is not the case, so this is not a solution to our differential equation. Maybe we'll have better luck with, 21, look at that. Y is equal to this. We do need y prime, so it looks like we're going to need to take a derivative of that, which means product rule. So if y is x squared e to the x, we're going to need y prime, product rule. And the product rule says we do the first, x squared, times the derivative of the second, e to the x is its own derivative, plus the second thing, e to the x, times the derivative of the first thing. Derivative of x squared is 2x. So there's our y prime. So let me move this up here. So let's see. Here we've got x times y prime. So we have x times this is our y prime. And I'm going to put it in here, x squared e to the x plus e to the x 2x. So that's this first part, and I'll switch over to black ink here. Now we've got minus 2y. Minus 2 times y. Well, y is x squared e to the x. X squared, x squared e to the x. And then we've got our equal signs. We want to see if that matches up with, let me block this off in green. We want to see if that's the same as this stuff here. So it looks like it's algebra time. We're going to distribute this x, so now that's going to be here in x cubed e to the x plus e to the x will distribute here, and that'll become a 2x squared. 2x squared minus, we'll just sort of distribute here, the 2 times this will just drop the parenthesis, 2x squared e to the x. So let's see what we got here. Well, let's see. We've got a 2x squared e to the x, and it's negative. And here's a 2x squared e to the x, and it's positive. So these two terms are going to cancel each other out. So these cancel out, and we're left with x cubed times e to the x. Remember, I didn't have enough room on the other side of the equals. Here it is, x cubed e to the x. So those do match up. This is a solution to our original differential equation. And then here in 29, we're going to find a particular solution. First, we're going to verify that the general solution does satisfy the differential equation, and then we'll find the particular solution that satisfies the given initial condition. If you're sick of listening to me, this is a red problem, so you could go check this one out on CalcView. So let's see. Here's our y equals, and we need y prime. So let's see, we're going to need the derivative of that, and that's it's a base e. So we're going to derive it with just a little chain rule. So our y prime is going to equal that same thing, c e to the negative 6x. But we will chain rule the derivative there of negative 6x is a negative 6. So we have a negative 6 appear in the front there. So now let's see if it fits this or satisfies this differential equation. Here is our y prime, negative 6, ce to the negative 6x power. We're going to add to that 6 times y. So this is 6 times y, and here's our y value. So in there goes a c e to the negative 6x. So we've got negative 6 of these plus 6 of the same thing, so those will cancel out. They do equal 0, and we were expecting that because the directions do say to verify that it is a solution. And now we want to find the particular solution that goes through the initial condition. So now we go back to our original equation here. And let's see, they give us y is equal to 3. So that 3 is going to jump in for that y. X is equal to 0. So that 0 is going to jump in right there. So let's see what we got. 3 is equal to c e to the negative 6 times 0. Negative 6 times 0 is 0, so this becomes e to the 0. Anything to the 0 power is equal to 1. So all of this just turns into a 1. 1 times c is equal to 3, so c is equal to 3. So using that info, getting back up here, this is our general solution. The general solution has a c in it, an unknown constant. Now when we write our particular solution, that's going to be the same as the general, y equals, but we're going to take out this c and replace it with our 3. 3e to the negative 6x power. So there's our particular solution. And just a couple more here to round these out. Find the general solution to these. So we'll just antiderive and get a plus c. Now it's kind of weird here. This is a good place to introduce what they call separation of variables. That's the heart and soul of 5-3 section. So when we're looking at 35 here, they give us dy, well I'm just not going to rewrite that, dy dx is equal to 12x squared. We want the dx's to be together with the x's. X's and dx's go well together, so do y's and dy's. So here, if we just multiply both sides by dx, the dx now appears on the other side. So we get dy is equal to 12x squared dx. Now we're going to do the same operation to both sides here. We're going to antiderive. So let's see here, the antiderivative, there would be a 1 in there, 1 dy. That's going to antiderive to a y plus c. And then on the other side of the equals, we'll antiderive this side with respect to x. So we'll raise the power by 1. That'll become 12x cubed. 12x cubed divided by the new power 3. And we'll add a constant. Now, we got a plus c on both sides. If you think we'll just subtract c from both sides, that would not equal 0. We're not sure that these constants are the same size. So what we would call this is c sub 1. The other one is c sub 2. And to get y alone, y equals this unknown constant added or subtracted to this other unknown constant is just going to be another unknown constant. So let's just get rid of this here, this 12 over 3, that'll be a 4x cubed, and then we'll just do a plus c. We could call it c sub 3 because we don't know the value of it, but it's different than these other two constants. So y equals 4x cubed plus c is our general solution. And then 41, same song and dance. We're going to multiply both sides by the dx. So now the dx appears on the other side. So let's see. We now have dy is equal to the sine of 2x dx. If I antiderive the left side with respect to y, that just becomes y equals. If I'm going to antiderive here, I first notice I do have an inner function. The derivative of that would be a 2 dx. So I do need to tweak this with a 2 and a 1/2 out front to get everything ready to antiderive. So here I'm going to have a 1/2. Let me move that over. 1/2. And the antiderivative of sine is negative cos. Negative cos of the same 2x. The rocket fuel burns up, and we just put on a plus c there. So y equals negative half cos of 2x plus c. And that's the last of the odd problems. I hope they helped.